Now in the Gauss's law or application of Gauss's law, now we will calculate the electric field due to hollow sphere. Let's see how we calculate it. Uh, in the first case, we have a conducting hollow sphere in one at the outside point. So to calculate the at a outside point electric field due to hollow conducting sphere, we take a Gaussian surface at a distance r from the center and apply the Gauss's law. Now here we have drawn a Gaussian surface, Gaussian sphere at a distance r whose radius is small r, and it is a hollow conducting sphere with radius capital R and charge q. Now we know that according to Gauss's law, phi net equals to, that is total flux equals to q enclosed by epsilon naught. So area of this whole sphere will be 4 pi r square, and if we consider electric field is E, then E will be into 4 pi r square equal to q by epsilon naught. Hence E equal to 1 by 4 pi epsilon naught q by r square. This is the case for outside the sphere. Thus for outside point charged hollow sphere behave as a point charge placed at the center of the sphere. Second case, at the surface we can put the value of r equals to cap r, and that will be the electric field at the surface. Here it is shown. So at the surface, E surface will be 1 by 4 pi epsilon q by r. Now third case, at inside point. For inside point, to calculate the electric field at a inside point of the conducting sphere, hollow conducting sphere, we take a Gaussian sphere of radius small r and use the Gauss's law. Now we can write for this Gaussian sphere phi net equal to qn by epsilon naught, or phi net, if there will be electric field, then E equal to 4 pi r square equals to, now q in, because here all charge is on the outer surface of the conducting sphere, so there is no charge enclosed by the Gaussian sphere, so q in will be 0. So 0 by epsilon naught equal to 0, because here 4 pi r square can't be 0 and epsilon naught can't be 0, so only possibility is that E must be 0, so hence E equals to 0. So inside a hollow conducting sphere, electric field is 0. Thus at inside point electric field is 0. The graph for electric field for a conducting hollow sphere is shown here. This is the electric field. On y-axis we represent electric field, and x-axis we represent distance. Now the graph is like here. If the distance is greater than r, E is directly proportional to 1 by r square, this graph show, or E outside is 1 by 4 pi, because E outside is 1 by 4 pi epsilon naught q by r square, and at surface it is constant. E surface equal to 1 by 4 epsilon naught q by r, which is, this value is maximum value, and inside the that is, if r is less than radius of the conducting sphere, then E will be 0, because then the point will lie inside the conducting sphere, and electric field is 0 inside the conducting sphere. That is, there will be no electric field inside the conducting sphere. Now potential can be calculated, because dV equal to minus E dr, so we use infinitive to outside point dV equals to infinitive to r E dr, or V outside minus B infinitive minus of infinity to r E outside dr, or minus of infinity to r 1 by 4 pi epsilon q by r square dr, or minus of 1 by 4 pi minus of q by 4 pi epsilon the r dr by r square, or minus q by 4 pi epsilon naught and dr by r square is equal to minus 1 by r infinity to r. So we have 1 by 4 pi epsilon naught q by r. So v outside, because v infinity is 0, v outside will be 1 by 4 pi epsilon naught q by r, because v infinity is 0 and 1 by infinity is 0. So using this value we get potential outside the conducting sphere, conducting hollow sphere 1 by 4 pi epsilon naught q by r, and electric field at surface will be using r equals to r. We get v surface 1 by 4 pi epsilon q by r, and inside the conducting sphere, that is v inside 1 by 4 by epsilon naught q by r equal to constant. This value should be constant because since E equal to 0 inside the conductor, so we can use E equal to minus dv by dr, and this will be only 0 when v equal to constant, and the value of v inside that constant value will be this 1 by 4 pi epsilon naught q by r constant. So it is shown in the graph different value at different position. That is, this shows the outside potential graph of potential versus distance outside the sphere. That is v out equal to 1 by 4 pi epsilon q by r. That is, v out is proportional to 1 by r. And at r, that is at surface and inside, potential will be constant and given by 1 by 4 pi epsilon naught q by r. Case B, non-conducting or insulating hollow sphere. That is, here we have hollow sphere, but it is not conducting hollow sphere, it is insulating hollow sphere, and charge is given on the surface of the insulating hollow sphere. When the charge is given to the non-conducting hollow sphere, all charge resides on the outer surface, and if the distribution is uniform, here we have considered that this charge distribution is uniform, the all cases will be similar to the conducting hollow sphere. Thus, this is the case when point is outside the sphere. We can solve same as is solved in the conducting hollow sphere. We take a Gaussian surface outside the hollow sphere and calculate flux, and then Q enclosed by epsilon naught. So E out will be 1 by 4 pi epsilon q by r square, E surface will be 1 by 4 pi epsilon q by r, and E inside will be 0. This is the electric field for different situation. And now potential outside will be 1 by 4 pi epsilon naught q by r, and V surface potential equal to 1 by 4 pi epsilon naught q by r equal to V inside. The graph will be same as for the conducting hollow sphere. That is, this is the graph for electric field and this is the graph for potential. Now electric field due to a solid sphere, a conducting solid sphere. The charge given to the conducting solid sphere will reside on outer surface of the sphere and will be uniform. All cases will be similar to the conducting hollow sphere. Thus, E outside will be 1 by 4 pi epsilon naught q by r square, solid conducting sphere for this, and E surface will be 1 by 4 pi epsilon q by cap r, and E inside will be 0 in the case of conducting solid sphere, because all charge resides on the outer surface of the sphere. So inside will be electric field 0. Using Gauss's law we can show this. So V E inside 0. Now potential will be same like at conducting hollow sphere. V outside will be 1 by 4 pi epsilon naught q by r, and V surface 1 by 4 pi epsilon naught q by r equals to V inside equal to constant, and it is the value of E and V is shown in the graph. Here E max will be at the surface, that is 1 by 4 epsilon q by r square, it is surface, and inside the surface, that is inside the sphere will be 0 electric field, so E equal to 0, and E out will be given by this graph, that is 1 by 4 epsilon q by r square. This graph shows the variation of E with r square. Again potential V inside will be constant and given by V surface and equal to V inside equal to 1 by 4 by epsilon naught q by r, and V out is given by this formula 1 by 4 by epsilon naught q by r, that is V out proportional to 1 by r. This graph shows this. Next case, conducting solid sphere. Now we have calculated conducting solid sphere graph, here it is shown. Now we will, our next case is that we have to find the electric field for non-conducting or insulating solid sphere, and charge is distributed into the volume uniformly, it is assumed. So non-conducting or insulating solid sphere, for outside point we have to take a Gaussian surface, Gaussian sphere at a distance r, and we have to calculate the total flux, and which will be equal to the q enclosed, which is equal to the q because this sphere has given charge q. So phi net will be q enclosed by epsilon naught. Now total flux, so the total Gaussian sphere will be into 4 pi r square equals to q by epsilon naught, and c equal to 1 by 4 pi epsilon naught q by r square, that is E outside is 1 by 4 pi epsilon naught q by r square. So all type of sphere, conducting, non-conducting, the outside point have same value of electric field, and which is given by 1 by 4 pi epsilon naught q by r square. That is the outside, for outside point the whole charge behaves at that it is concentrated at the center of charge, that is behaves like a point charge. Second case, at the surface of here it is also given by surface 1 by 4 pi epsilon naught q by r square. At surface this value will be. Now next case is inside the solid sphere, insulating solid sphere. Here the situation will be different. The third case inside the sphere. Now because charge is distributed uniformly to the whole volume of the sphere, so for inside point we have to take a Gaussian sphere at a distance r to calculate the electric field at a distance r from the at a point P. So this is a Gaussian sphere. Now we should calculate the charge enclosed by this Gaussian sphere, and then use the formula Gauss's law, that is total flux through this sphere will be equal to Q enclosed by epsilon naught. So first calculate the charge enclosed by this Gaussian sphere. We know that here given volume charge density rho equals to Q by 4 by 3 pi r q, that is charge by volume. The sphere has volume r, radius r, so volume will be 4 by 3 pi r q. Now if q dash be the charge enclosed by the Gaussian surface, we are considering that charge enclosed by Gaussian surface is q dash, then the value of q dash will be q dash equal to volume of Gaussian sphere gune surface volume charge density. So now volume of Gaussian sphere will be 4 by 3 pi r q into q by 4 and density, volume charge density rho is q by 4 by 3 pi r q. Here this value is calculated. So this will cancel. We are left with q into r q by r q. So now from according to Gauss's law, we have phi net, that is total flux equals to q, total flux through the Gaussian sphere, q enclosed by epsilon naught, or E equal to E into 4 pi r square. Because it is symmetrical situation, we already have earlier proved it, that it flux will be like this. E equal to 4 pi r square equal to q dash by epsilon naught. Now so E will be equal to, this implies 4 pi epsilon naught q dash by r square, 1 by 4 pi epsilon naught, putting the value of q dash is this value, So q into rq by rq into r square, or 1 by 4 pi epsilon naught, that is r square will cancel r square and only one small r left. So 1 by 4 pi epsilon naught q by rq into small r. So electric field inside the insulating sphere will be 1 by 4 pi epsilon naught q by rq into r, that is E inside is directly proportional to r. Now similarly potential can be calculated. V outside will be 1 by 4 pi epsilon naught q by r, and V surface will be 1 by 4 pi epsilon naught q by r. Now V inside the potential we have to calculate, because charge is varying at every point. So calculation of potential inside the solid sphere. Solid insulating sphere, it should be kept in the mind. If only solid insulating sphere, and for conducting sphere it will be constant. So we know that dV equal to minus of E dr. So we have to calculate inside point. So infinitive to P, dV equals to minus of, first we integrate it from infinity to on the surface, so infinity to r E out dr. During point is near to the surface or at the surface, so we can use formula for E out. So E out dr, and plus now from we are integrating going from r to distance r, so our integration is from r to r for inside point. So electric field will be E inside dr. So Vp minus V infinity will be minus of under bracket infinity to capital R1 by 4 pi epsilon naught q by r square dr, plus r to small r 1 by 4 epsilon naught q by rq into r dr. Now this implies potential at P inside the point will be equal to minus of q by 4 pi epsilon naught integration of dr by r square is equal to minus 1 by r, and infinity to r plus q by 4 pi epsilon naught rq, and integration of r dr is r square by 2. So and limit is from r to r. So minus of under bracket minus q by 4 pi epsilon naught q 1 by r minus 1 by infinity plus q by 8 pi epsilon naught r, taking 2 out of the end, r square minus r square, and so this will be, when we take inside the minus sign, this will be positive and this will be negative. So q by, and this will be 0 again. So q by 4 pi epsilon naught r minus of this value q by 8 pi epsilon naught rq into r square minus r square, or q by 8 pi epsilon naught rq, taking common this value, here will be 2 r square minus under bracket r square minus r square, or q by 8 pi epsilon naught rq into, this will be minus minus plus and this will be minus, so 3 r square minus r square. So this is the potential inside the insulating sphere given by this value q by 8 pi epsilon naught rq into 3 r square minus r square. Now from the graph it can be shown. Here we see that in the, for the electric field we see that inside the electric field here E inside is 1 by 4 pi epsilon q by rq into r, that is this will be a straight line, that is E directly proportional to r, so this will be as a straight line. Now at r equals to r, it will be given as q E maximum 1 by 4 pi epsilon q by r square is surface at this value, this will be maximum, and outside the point this will be given as 1 by 4 pi epsilon naught q by r square. Similarly potential, the value of potential will be calculated like this. Inside the sphere, that is inside the sphere, this value is given by this formula 3 by 2 1 by 4 pi epsilon naught q by r. or 3 by 2 Vs, and at the surface will be Vs equal to 1 by 4 pi epsilon naught q by r, and outside it will be given by formula uh, and outside it is given by this formula, uh, formula of this formula, q by 8 pi epsilon naught r q into 3 r square minus r square. This value is constant, and this that is proportional to r square, negative of proportional to r square. So this will be like this potential. Next,